All right. All right, good afternoon, everybody. My name is Minhan. I'm a software engineer at Google, and my co-speaker is Ping. She's a software engineer at Intuit. So we're here to talk about pod readiness and pod readiness gates, and we're here to explore their meanings and their usages. So we have 4 parts. One is the quick recap on pod status, and also an intro to pod readiness gate, and a usage at GKE and at Intuit. So quick recap. So Kubernetes API exposed rich set of container status. So here's an example of container status. Here, like it has image IDs, like container runtime IDs underneath, and it explicitly has a readiness per container, and also the state per container. And Kubernetes also let users to define liveness and readiness via the form of liveness probe and readiness probe. So each container gets to define, okay, a liveness probe and a readiness probe. And kubelet will execute this probe on the local node. And for liveness, it basically signals whether kubelet has to kill the pod and restart it, or kill the container or restart it. And the readiness basically reflects if the pod is ready. And also, there's a rich set of pod level status. So there are pod scheduled, which means that if the scheduler has already scheduled the pod. Pod initialized means that if there's like all the init containers in the pod are like actually successfully started. And finally is readiness, right? Whether all the containers are actually ready or not. So here's a quick example of a pod lifecycle. So here is a pod with 2 containers. If no liveness probe is specified, then it's live by default. So you can see when the pod is started, both containers are considered live, and container 2 first becomes ready, and then container 1 becomes ready later. Then the pod becomes ready, and it starts serving traffic. And when the pod is deleted, a SIG term, kubelet will gonna signal both containers a SIG term signal, and then they will gracefully shut down if the container image can handle it. And then when the graceful termination period is done, then kubelet will basically signal a SIG kill and kill the pod. So what does pod readiness mean? Pod readiness means that all containers are ready, and then the pod is ready, then pod is ready to serve traffic. And what are the meanings it has? So each consumer of pod readiness is actually effectively extending its definition. So here we look at workload, and specifically we wanted to take a look at deployment. And in deployment, you can specify the rollout strategy, where you can say, hey, what's the max surge and max unavailable? That basically configure how fast you wanted to proceed the rollout. And what happened underneath is that the deployment controller will actually control like multiple, in one case of a rolling update, it's gonna be juggling between 2 replica set. And in this example, it's in the middle of a rollout, and you can see generation 1 replica set has replica 5, and generation 2 replica set has replica 5. That means we have 5 old pods and 5 new pods. So here's a typical workflow of the rolling update. You can see pod 1 gets created, and pod 1 gets scheduled, and kubelet watches the pod that is scheduled on its own. And kubelet runs the pod and start the pod onto the container runtime, and container runtime reported success. Then kubelet says, oh, the pod is ready. And when the pod becomes ready, and deployment controller observe the pod readiness via like a replica set, and then it makes a decision to say, hey, it's time for me, based on the deployment spec, the rollout strategy, whether I should proceed to the next pod. And in this case, it says, okay, the pod 1 is ready, then I should proceed to the next one, which is pod 2, and then pod 2 go through the same cycle. As you can see, pod readiness is a core signal for deployment decision making. Well, similarly, service is also a consumer of pod readiness. And and pair with service is the endpoints object, and the endpoints object contains all the endpoints behind the service. And for all the endpoints, for all the pods that are ready, it should be contained into in this endpoints object. So this is a typical endpoint update flow. So when the service is created, the endpoint controller is already automatically creating the corresponding endpoint object. So when the service is created, the endpoints already exist. The pod gets started, pod gets scheduled, then kubelet sees it, and kubelet starts the pod and reports the pod ready when the container runtime, everything is in shape, or the readiness probe reporting ready. And then endpoints controller are watching all the pods, and it sees this new pod belongs to this service has become ready. Then the endpoint controller updates the endpoint object, and the endpoint, once the endpoint object gets updated, it's reflected, this new endpoint is ready in the endpoints object itself. And the endpoints object will be distributed to all the kube proxies, and the kube proxies will further implement the actual load balancing mechanism underneath. Is either IP tables or IPVS or eBPF or whatever kube proxy you use. And then finally, the endpoint is programmed. So you can see the color coding. The blue state means the older state. The green state is the actual intended state in various dimensions. So if we look closer, the endpoint status is actually not feedback into anywhere. So it's just programmed. It's sort of like a best effort. And obviously the endpoint, whether the endpoint is programmed or not, does not reflect back into the pod readiness. And you can see there's a gap. There's actually a programming latency from the pod becomes ready, and the endpoint is actually getting reflected in IP tables or IPVS. And also combined with the fact that it's a cluster, it has many nodes, and then each node, you have to program each node to actually reflect it. So there's a programming latency between the pod becomes ready and is reflected globally in the cluster. So what is pod readiness? It's a core signal to workloads. It's either Kubernetes native workloads, third-party workloads, operators, they all look at pod readiness. And also, it's also a key signal to networking, abstraction, services, ingress, because ingress reference services, so inherently rely on pods. And also network policy, although network policy does not rely on pod readiness, but it needs to be programmed. So effectively, pod readiness is the rendezvous point of the whole Kubernetes API ecosystem. So actually, do these APIs work together, right? Intuitively, they should work together. If they don't, why do people actually adopt Kubernetes? Why do we have such a big KubeCon, right? So the answer is yes, but not without caveats. So if we look closer, workloads and pods have a closed feedback loop. That means workloads, they manage the pods, and they also observe the pod. They rely on the pod readiness for their internals, either for rolling updates or reacting to changes. For instance, the node goes down, and then you wanted to maintain the certain healthy, the certain ready available replicas, then you were gonna schedule more pods, which runs elsewhere, right? And on the other side, the relationship between pods and the networking abstractions are actually one directional, right? So a single directional relationship. So if, let's say, if the endpoint is programmed, there's nothing to feedback it back into the pod, or whether the network policy is actually enforced, there's nothing you can feedback into. It's sort of a best effort. So why this hasn't been a big problem so far? Why does one directional relationship between the pods and the networking aspect? And then there's and then the workloads effectively ignores the networking abstractions. So this is mostly thanks to the robust implementation of kubeproxies and the underlying API machinery. So from what we have observed is that in a like normal cluster not under load, it's pretty reliable and fast to update a single endpoint. Usually it's less than 5 seconds, and the new endpoint will get reflected globally in the cluster. And not much user, a Kubernetes user has like complained about it and say, hey, we have like the endpoint update is too slow or something like that. And it's very unlikely to hit the corner case, something like my deployment is done and I have rolled out all my new pods, but my service is still pointing to my old pods, right? This is pretty weird, or like very small cases like this. So here comes the pod readiness gate. So Kubelet dictates pod readiness so far. Readiness probe only executes on the node, and there's no external feedback allowed to influence the pod readiness. So what if Kubelet is not capable of determine whether a pod is ready or not, right? And secondly, what if we want the workloads to be network aware, meaning that, let's say, when I proceed the rollout, I want to make sure that everything is ready. What I mean everything is ready is that endpoint is ready, network policy is ready, everything related is ready, right? Before I proceed, not only what Kubelet tells me is ready. So, and finally, there are more sophisticated service health management solutions which incorporate more application level metrics like latencies and things like that. How can they better integrate with Kubernetes internals? So can we do something like pod ready plus? And when we look at, when we are trying to solve this problem, and we actually face a lot of constraints. So the constraints are mostly summarized to backward compatibility, and backward compatibility. So Kubernetes APIs have been well adopted, and many people are running in production. And although current system is not perfect, but it works, right? It works most of the time. So how can we introduce a new pod ready plus mechanism without breaking the backward compatibility? So some of the concerns are like how to make it work with existing pod specifications, how to make it work with existing kubelet control flows. And I don't want to inject overly complex kubelet control flows, so that because kubelet runs everywhere, it should be reliable, and yeah, it should just work. And also, how can the mechanism work with existing workflows, right? There are many different workflows. There are replicas that like Kubernetes native ones, deployment, stateful set. There are user-defined controllers. How can we make this change without changing all these controllers? And finally, how to make it transparent to the user so that the user is not aware of this new change. And the pod readiness gate was proposed and implemented, and it's now GA'd since Kubernetes 1.14. And here's an example of the pod readiness gate configuration. It has two parts. One is in the pod spec. One can specify a list of pod readiness gates, and the pod readiness gates are each pod readiness gate reference a pod condition. And in the pod status, the pod conditions are indicating whether the readiness gate is actually ready or not ready. In this particular case, although I did not basically, let's assume all the containers are ready, and you can see that readiness gate 1 is false. The status is false, and readiness gate B is true. So that means readiness gate A is not ready, and that means the whole pod is not ready. So we effectively change the pod lifecycle into this graph, right? You can see when the pod starts up, nothing's ready. So then, even though container 1 and container 2 both have become ready, pod is still not ready because it's waiting for readiness gate B, right? So only when everything is ready, the pod is considered ready, and then it starts serving traffic, and and then the rest of the life cycle is the same. So with pod readiness gate, pod readiness means all containers are running, all containers are ready, and all pod readiness gates conditions are true. So in order to capture the existing pod readiness, which means like all containers are running and ready, we introduce a new pod condition, which is called containers ready, right? So when the containers are ready, then it preserves the old definition of pod readiness, which is all containers are ready. So whoever wants to consume like this can switch to consume the containers ready condition. Well, so far we talk about the API. How do we use it, like with a seamless user experience? So there are two parts. One is how do you inject the readiness gate? As you can see, it's a part of the pod spec. Well, there are already pretty mature mechanism to inject stuff into like any object in Kubernetes, that is webhooks. So if you have some kind of infrastructure or platform specific readiness gate you want to inject, write your own webhook. And then how to update the readiness condition, right? Because so far only kubelet gets to update the pod conditions, pod statuses. So as part of these, the pod readiness gate, the kubelet it has been changed to use patch to update pod status. It will ignore like the fields that it does not belong to. So it does not own, like kubelet owns certain fields and it leaves the other fields to other components. So that means you can use patch to update a single condition in a pod. And this will actually cause no conflicts, and also there will be no race conditions since the fields are separately owned. One part of the pod status is owned by kubelet, and then something can own the pod readiness gate condition. You can even do it in a custom controller, and then that automatically reflects the condition. And as part of the pod readiness gate change, kubectl has been like a new field has been added. It's called readiness gate. So we decided not to change the existing ready column because so many tools and so many people are relying on it. And kubectl get pods, it's sort of like the mostly executed kubectl command. So we don't want it to change it. If, let's say, many people are adopting pod readiness gate, so we can revisit this decision. So you can see there's a separate column, and like the ready column means that how many containers are ready for the pod, and the readiness gate column means that how many reflects how many readiness gates are has status true. Okay, so let me talk about the Kubernetes engine use cases for pod readiness gate. So we use it extensively for the container native load balancing feature we have. So on the left is how a typical cloud load balancer integrates with Kubernetes. So the load balancer does not know pods. Load balancer basically targets the cluster nodes, And then typically, the load balancer points to the service node ports. And the node port type service, because it exposes a consistent port on all the cluster nodes, any traffic flows to that node port will be like randomly forwarded to one of the backend pods. So on the left, the typical case is that there's a secondary load balancing happening on the nodes and further deliver the traffic to the backend pods. So this setup actually has many downsides. It's actually worth a complete talk to describe the problems. So we're not going to do it here, so probably next time. On the right is what we call container native load balancing. So the Google Cloud Load Balancer can actually target arbitrary endpoints. So it has a new construct called network endpoint groups. So you just need to put the endpoints into this construct. And load balancer can directly send traffic to the pods. So it has many advantages. So obviously there's no second hop. So pods become first class endpoints. And also the cloud load balancer features just works. Like for instance, traffic shifting, cookie affinity, and things like that. Like for instance, the traffic shifting, right? If you are doing the secondary load balancing, if you shift traffic among VMs, it doesn't translate to shifting traffic among the backend pods because any VM will just randomly forward traffic to one of the backend pods. So with this container native load balancing, you can actually accurately shift traffic among the pods. And also, it can evenly distribute the load accurately. Because consider, let's say if the load balancer is targeting the VMs, so the load balancer is basically doing traffic accounting per VM, the load balancer thinks that, I'm perfectly balanced, and then I'm going to send traffic to my backend in a balanced way. But actually, because of the secondary load balancing happen on the node, it messes up that accounting, and then it becomes irrelevant. And with this direct targeting, so it's better balanced. But however, it's not without its challenges. So the classic setup just needs, for an endpoint update in the classic setup, we just need to update the IP tables. And update IP tables is pretty fast, right? From what I just mentioned is like less than 5 seconds. But when you're talking about programming an external load balancer, it's a different story. There are many flavors of load balancer. There are regional. There are for Google Cloud, it provides a global load balancer. That means a single pod, a single endpoint change, it needs to program a globally distributed infrastructure on all the Google edges. And it's definitely higher than 5 seconds. So for the extreme case, since the pods can start up very fast, depending on your container image, some image can start at less than a second, and it starts and it becomes ready, then the deployment say, I can just proceed, and then within seconds, your backends can finish rollout, right, within seconds. But the load balancer is not actually completed the programming for the new endpoints. So in that case, your old endpoints are all gone and your new endpoints are not programmed. That would, in the extreme case, that it will cause an outage. So how we solve it? So here, we're going to walk through a rolling update case. So on the left, the blue replica set is the V1 replica version of the application. And the green one is the V2. So at first, everything is stable. The load balancer is targeting the old version. Then let's say the rolling update starts, right? The new pod gets started, and from the pod, it becomes ready. The containers becomes ready to serve, but the load balancer is still not programmed to target the new pod. And the old pod gets removed. In this case, in this transition period, there's a slight reduce of the capacity because it used to be 3 pods serving traffic. Now it's only 2. And however, Kubernetes deployment will not proceed because pod is not ready because there's an extra readiness gate to reflect whether the infrastructure is ready. So the Readiness Gate will wait till the Google Cloud Load Balancer to say, hey, I'm ready for this new endpoint. Once is this ready, the Readiness Gate condition will reflect that. And Kubernetes workload and the cloud network infrastructure will work together seamlessly. You can just use the native Kubernetes workloads to manage this, the cloud infrastructure. With all that, I wanted to pass the mic to my co-speaker, Ping. She's going to talk about the use cases at Intuit.
First, thanks, Minhua, to invite me to present how Foremast leverage Pod Readiness Gate. Let me first briefly introduce what is the Foremast and why is the Foremast. Foremast is Intuit-sponsored open source cloud-native platform for observability to monitor the application health in steady state operations running on Kubernetes. It leverages metrics, logs, tracings as observability signal. It also uses AI-based anomaly detection and can perform auto remediation based on once anomaly is detected. So now let's talk about Pod Readiness Gate with Foremast use case. So today I'd like to introduce two of use cases we can leverage. The first one is continuously health check. So Foremast not only can monitor the application health, but also pod health based on the golden sign signal. Once Foremast detects particular pod is unhealth or anomaly, so we leverage Pod Readiness Gate feature to set pod readiness condition to false. So in this way, the pod can that particular pod can take out of traffic. Then people can debug and troubleshooting it. So the second use case is avoid false alert. So in the past, we found once right after pod ready and pod start to serve the traffic, at the very beginning of first 1 to 2 transaction, appears have high latency or sometimes even run into like a error timeout. That is because of application may some of applications components, some of the component may still not fully initialized or some depends on some external dependency. So we introduced the pod readiness condition feature. So first we checked readiness resource signal is if it's ready, and then set pod readiness condition to true, and then start to serve the traffic. So today I'd like to have a demo of the second use case. This is a brief demo flow. So I mark the step 1, 2, 3, 4, 5. So first step is when we start a demo, V1 application is deployed. And the second step is we start to deploy V2 to replace V1. And now V2 is deployed, and the pod is ready. And then we add additional readiness resource check for V2, and then set a V2 pod readiness condition to 2. Between 3 and 4, pods start to serve the traffic. 4 to 5 is we find application have a high error spike. So the light or orange solid line is indicate we have the machine learning model. This is the upper bound, which is generated based on historical data. So in number 5 is Foremast detect anomaly and issue the auto remediation, which is a rollback in this case. Number 6 is V1 is replaced to V2. So V1 application is like a deployed, in this case. Let me have a real-time demo for it. Yeah, step 1, just like I mentioned on the demo flow. So application is the demo, version is V1. Is deployed. No, this is just display the V1 pod name. And still step 1, I just give you more information. V2 is not there. Step 2, we start to deploy V1 by, replace deployment of V1 by V2. So, okay. So you can see the deployment is replaced. Yeah, here is just indicate application is now, version is, application is demo. It is V2 already. Now, let me display the pod. So you can see the V2, I set the pod readiness. So here, the second graph is the readiness resource check. So now the readiness condition is set to 2. You can see 1 of 1. V1 got a terminator here. Now applications start to serve the traffic. Yeah. Let's see. You can see we have a ETS, and also we have the error matrix here. So here, because error appears high, so Foremast indicate application is unhealthy. I missed one. So our remediation is auto rollback. So now let's display what is the deployment version is rollback to V1. Here's some more information. Here is the V1 pod. And then here just display V2 is like there's no V2 pod anymore. Yeah, that's the demo. You can see the first top of graph is like V2 is replaced by V1 once anomaly is detected. Yeah, here is the Foremast team. Foremast is an open source project. Welcome to join the Foremast.
All right, cool. So that concludes our presentation. So, yeah, question?
Yeah, I think technically we're out of time, but they'll probably be here for a couple minutes afterwards to take questions up here. Again, please, thank you for coming, and remember to rate the session on your app. Thank you guys very much.